Hello, welcome, ladies and gentlemen, once again to another Nanosurf webinar. I'm Daniel Hartmann from Nanosurf's headquarters in Liestal in Switzerland. And today we will focus on a topic we actually received many requests to hold a webinar about over the past half year since we've been asking for topics. And Dr. Patrick Frederix will show us the ins and outs of Piezo Force Microscopy today, explaining the physics behind the mode, how to perform it on a Nanosurf instrument, and also some application examples, of course. This is the first webinar we're holding at only a single time in the day. We changed to this, so we were again able to hold the webinars live and in the future to make them more interactive. So if you have any feedback or input and ideas regarding this, please do let us know and we'll try to make use of that. One last thing before we get to the presentation, just to submit a question for us to answer in the Q&A session at the end. Please find the Q&A panel in the GoToWebinar controls and use that to submit your questions instead of the chat. That allows us to structure our answers better. You just use the chat if you have technical issues. I'll try to take care of them and help you, or off-topic things. So now let me introduce today's speaker. He's already here with us, Dr. Patrick Frederix. He's the head of our applications team and a very experienced AFM user, and he's been with Nanosurf for about 11 of the 20 years he's been working in the field. And with that, I'll let you get started, Patrick.
Okay, thank you very much, Daniel. And I also wish you welcome to this webinar. And let me get started and immediately. So today's subject is piezo response force microscopy, abbreviated with PFM, and I want to go into some of the background issues and some examples of this method. So first, shortly, we offer the PFM mode on 3 different system lines. The Drive AFM, which was released end of last year, the Flex AFM, which is already since more than 10 years on the market, and also the Core AFM is compatible with PFM mode. Now let me start with a short introduction about PFM. I guess most of you might know it, but for those who don't, here a short introduction to it. Piezo response is related to the piezo effect, and the piezo effect is if you apply a mechanical stress, here denoted by the blue arrows, on a sample, this sample can create a voltage which one can measure. And more relevant for the topic today is actually the inverse piezo effect. That is, if you apply an electrical voltage here, you will see a mechanical change of the sample. The sample is either extending or shrinking or moving, and this is something we can nicely measure with the AFM. Where are piezo electric materials used? There are sensors that really let you push on it, and the mechanical stress is giving you a voltage. But they are also in ultrasonographs, where you have a transducer to look through inside the belly of a woman to look at the unborn child. Hearing aids, where you have a piezoelectric transducer getting the sound waves transferred into a mechanical movement that can be then transferred to the ear. But there is also sensors, ceramic capacitors, resonators, and the sensors are, for example, also used in car parking devices. So if you are backing out your car before you hit an object, you have the sensors in, and these are also using piezoelectric materials. So there is a wide field of applications. In AFM, Of course, most AFMs use also piezo technology because most scanners used in AFM are based on piezos. Yeah, what can be learned from a PFM experiment? You can basically it's used for the characterization of ferroelectric or piezoelectric materials down to the nanometer scale, so well below the micrometers. Laterally, that is the resolution, but vertically, we even go well below that. And if you do that, you can try to measure the domain walls between different domains and their intrinsic properties. You can try to measure the influence of extrinsic contributions to the dielectric permittivity and piezoelectricity, domain wall pinning and at this location and grains. And for quantification, you can try to determine the piezoelectric coefficient D33 or D33. In this case, with units picometers per volt, quantifying the volume change when a piezoelectric material is subject to an electrical field, along with its polarization. And why to do that with an AFM? There are many new challenges with objects getting smaller and smaller, and now also giving smart materials where they try to combine different properties into, for example, flexible glass. And there, if things get smaller and you want to characterize them, you need higher resolution. Very late application of the PFM imaging mode is actually is to study the angular mismatch between single layers of 2D materials. If they are not exactly matching, you'll get a moire pattern, and this can be made visible using the PFM imaging mode. But now about the implementation of PFM. In general, PFM is operated in contact mode to measure the topography. So you have your sample in magenta, a cantilever in yellow on top, a laser shining on the back of the cantilever, and the reflected laser light is getting on a quadrant photodetector, so that if the cantilever is bending up or down, the light is shifting on the photodiode and you can see that as a deflection. Now that signal is then processed by a controller, and you can use the controller for imaging, spectroscopy, and the data analysis. Let's start with out-of-plane PFM. And with out-of-plane PFM, we mean that you apply a vertical field through this magenta sample, and then if the polarization of the piezo material is parallel to that, you get an extension of the height of the sample. If there is an AFM tip on top, this AFM tip is pushed up and the laser light is moving up. However, if the polarization is anti-parallel, the sample is not extending, but it's rather shrinking. The cantilever is going down and the laser will go to the lower half of the readout sensor. Typical displacements are way below 100 picometers per volt. That means even with 10 volts, you get only a few nanometers. And even more practical or realistic is that you only have a few tenths of picometers of deflection. And that is not so trivial to measure. So what you often do with AFM is, if DC is difficult, and that is difficult for such small signals, you use AC, and you create an AC field over the sample. So if you do that, the field goes from vertical to downwards to upwards, and when it's downwards, it's parallel. When it's upwards, it's anti-parallel, and you see that the sample will start to vary oscillatory in height. And if the cantilever is on top, the deflection is moving along with that. if you have a strong piezoelectric material, you get a high deflection amplitude. If it's a very weak piezoelectric material, you get a very small deflection amplitude. What happens now if I have the same field, but the polarization of the sample is the other way around? So left, the polarization is downwards. Here on the right, the polarization is upwards. What you see is that the deflection is moving more or less with the same amplitude in this case, but the phase has been flipped. And this is what you can immediately see. If you have a sample with different polarizations in it, you can see there should be 180 degrees phase shift between oppositely polarized directions. And that's also what we can measure with the AFM. In addition, as mentioned, the amplitude of the deflection will depend on the magnitude of the piezoelectric effect. And how do we detect that? It's now an oscillating signal, so we can use the deflection, put that into a lock-in amplifier. And now on top of this static mode setup that I showed before, you now get that the deflection is fed into a lock-in amplifier inside the controller and gives you the amplitude and the phase of the oscillation. How do we create the electrical field? So far, I just draw a line. There is an electrical field. Generally, the AFM tip is used as one electrode. The substrate below the sample is used as the second electrode. And you can now apply AC and DC voltages between the tip and the electrode. It's both possible to have the sample at ground and apply these signals to the tip, or to have the tip at ground and apply these signals to the sample. And what I've observed is that generally you get the nicest contrast if you keep the tip at ground and you apply the AC voltage to the sample substrate. And as said, amplitude phase are measured by the lock-in amplifier. And you can now measure locally where the tip is on the sample, what the piezo response is, giving you the high spatial resolution that you want to have. Okay, very nice, but I have just a material, and who says that the material is perpendicular to the surface? The vector could in principle be parallel to the surface. And in this case, I've drawn the case where the piezo polarization is in the plane of the sample and perpendicular to the cantilever length. So here you see the cantilever from the front. If you now apply this electrical field, the top surface will move to the left, and you see the cantilever is starting to twist. It's starting to bend sideways. As a result, the laser is moving sideways on the photodiode. And if the polarization is in the opposite direction, the laser goes also in the other direction. Similarly, as in the previous case, you can now also reverse the polarization directions of the field directions and mirror these two images. So you can also apply here an oscillatory electrical field, and you get a movement, a lateral movement of the cantilever. Polarization can be detected from the phase, and again, the magnitude gets from the amplitude of the oscillation. And there you can use a second lock-in amplifier of the controller. But again, I took an assumption before I had it out of plane. Now I took it, yeah, it's in plane, but perpendicular to the cantilever. What if it happens to be parallel to the cantilever? And now it's getting a bit more complex, because what happens now is, yes, my surface is again moving to the side, but now if the cantilever is from left to right, you see that a movement of the surface to the left will bend up the cantilever, and the deflection signal will go up. And oppositely, if the surface moves to the right, the reflected beam from the cantilever will move down on it. So this is a signal that is in the same direction as the one of the out of plane signal. So they clearly intermix here. So it's causing a vertical deflection. What you should notice, this is not the same kind of movement that you have when the sample is directly pushing vertically on the cantilever. It's actually a kind of a buckling movement. The tip is moving sidewards, rotating the end of the cantilever, and that gives you a different type of movement than the normal vertical movement. But of course, also this might be a too high simplification. So in first case, we had the black line where the polarization is perpendicular to the cantilever. But as we have seen, it can also be parallel to it, but more realistic, it will be in some direction. What you can do now is try to rotate the sample, find the same area and scan that again. And what is here parallel to the cantilever is suddenly perpendicular to the cantilever when you rotate the sample. The advantage of this is that the signal perpendicular to the cantilever can be detected by the lateral deflection and is not intermixing with the vertical deflection. And if I do both measurements, I get the black vector, I get the white vector, and in the end, I get my green vector, my total signal out of it. If you would have a sample without any component vertically out of plane, you might do it in a single measurement, but it still needs this buckling deflection sensitivity to be known. And of course, in this case, the black one in the top and the white one in the bottom, there you can assume that they use the same deflection sensitivity. It's in both cases a signal perpendicular to the cantilever. And that gives you the total in-plane piezo response. And if you then also have the out-of-plane response, then you can get the total 3D vector of the PFM signal. But remember, it requires that you are imaging at the same position. And for quantification, you need to be able to quantify the signals. I have a slide on that towards the end of the presentation. Oh, what's happening? Okay, let's give some examples. First example, what I want to show you here is an example of an out-of-plane PFM. This is a commercially available sample sold under the name PFM03. It's oppositely polarized lithium niobate. It has stripes with upwards and downwards polarized lithium niobate. That means the topography, you don't see anything on it, but the PFM response clearly depends on which you are. The repetition of the stripes is about 10 micrometers. And what you see here is the phase image of these areas where you clearly see bands in red with one polarization and in yellow with the opposite one. And here on the right hand, you see two line graphs through the image. In the bottom, the phase where you nicely see the 180 degrees. And this is the data as imported from the AFM. So I didn't do any post-processing to normalize it to 180 degrees. I only added an offset, but for the rest, the 180 degrees is there. Since it's the same material in the yellow and red areas, you don't expect a large influence on the amplitude by the polarization. It's the same thickness, about 500 micrometers everywhere. And that's also what you see here in the profile of the amplitude, whether you're on the red parts or on the yellow parts, which are wider, you get almost the same amplitude. And yes, of course, at the boundaries between them, the amplitude drops almost to zero. This measurement was recorded with an AC voltage of 5 volts at 23 kilohertz. And this was done by a student we had here in the lab, Brian Odermatt, who did an internship at Nanosurf. A second example, this is CIPS, copper indium phosphor sulfide, placed on a silicon wafer that forms nice flakes. You can put them with the top view camera. You can put the cantilever on top of a flake and then you can measure it. On the left, you see the amplitude. In brownish, a very low amplitude, yellow, white, a much higher amplitude. And in the right, again, with the yellow-red scaling, the phase. It was nicely, again, 180 degrees phase shift. And I used here the normal deflection sensitivity of that you can either record with force spectroscopy or contactless, combining Sader and the equipartition theorem. And you see that in amplitudes are in the tens of picometer range. So you see areas with different amplitude, different phase. And of course, the next question is, yeah, but how do they relate? You can see, yeah, there is some white that's probably somewhere there. And one way to get an easier representation of the data is to take a so-called projection, which is the amplitude multiplied with the cosine of the phase. Since the phase is either 0 or 180, it means that you multiply the amplitude with 1 or minus 1. And if you do that, you get this area. In black, you have almost no amplitude. The magenta is a positive high amplitude and green is a negative high amplitude. So here you nicely see the different amplitude plus phase or amplitude with an added sign to it. So you easier see the combination of polarization and amplitude information in one single image. Yeah. And this was imaged with 3 volts of AC amplitude. An example of in-plane PFM. This is a sample we got, which one of our Brazilian customers measured. And you have these domes on the surface. It's lead zirconate, titanate, PZT thin film grown by Sol-Gel. It's on a flexible glass, so it's they're going towards functional materials, and they want to look at the 3D PFM response. Left top is the topography, where you nicely see the domes. Here on the right, you see the PFM projection of the out-of-plane contribution. And since I now wanted to focus on the in-plane, here in the bottom, you see the in-plane signal with high positive and high negative values, which just means that the green and the pink magenta have opposite phase. So is that all you can do with PFM? Now there are a lot of different ways to perform it. This was now all off resonance. And off resonance means that if you have a resonance of the cantilever of, say, a typical EFM cantilever would have 75 kilohertz, then here we worked at 23 kilohertz sometimes, or in that range. Can also be 13 kilohertz, just different values well below the resonance. Since we are in contact with the surface, it's not really the normal resonance that's important, but the contact resonance. There, the tip is also in contact with the surface, and you get a different mode of movement because you have now both sides of the cantilever fixed, are not freely moving, and then you get the so-called contact resonance, which is 4 to 5 times higher than the normal resonance. And if you work at that resonance, you see I get at the same excitation amplitude, I can get a much higher response. And if you do that, you can consider now the sample, which is a piezo material, as kind of a shaker piezo. So you oscillate the sample, and if you are at the contact resonance, you get an amplification of this oscillation. And again, this cantilever doesn't make the normal oscillation that you are used to from tapping mode. It's also a buckling movement with the tip almost at a fixed position, moving a bit by the sample, but the belly of the cantilever making a much larger movement, which gives you an angular change that is detected by the laser. This, of course, also affects the deflection sensitivity. And that means that if you want to quantify the amplitude here, you not only have to take the quality factor into account from baseline to the peak, but you also have to take into account that you're now working with a different movement mode, where you have a different relationship between vertical displacement and angle. This is a measurement that Sergei Maganov did a few weeks ago. He's currently visiting our lab. And here on the left, you see the amplitude. And here on the right, you see the phase of a piezo response. It's also PZT sample with small amounts of a donor dopant of lanthanum 3+, for improved fatigue and retention properties. Size is only 3 by 3 micrometers. A 5 voltage was applied, and now it's not at just a few tens of kilohertz. It's at 300 kilohertz. That is 4 to 5 times the base resonance, and that was the contact resonance of this cantilever. The sample is from Portugal, as you see there, the Cortesy. And what you nicely see in the phase is that also very small objects. So this peak here is about 100 nanometers wide, but if you look here in it, there is also smaller objects in it. With PFM, you can get a lateral resolution well below the 100 nanometer dimension. Contact resonance PFM, however, can be tricky, because what happens if I have a mechanical interaction between my tip and my sample, and this interaction is changing, either because of mechanics or because of electrical properties. In that case, the contact resonance would move. If that moves, that gives you immediately a change in amplitude and a change in phase. The change in phase is probably not that big, but the change in amplitude can be significant. And that's why you can use so-called dual frequency resonance tracking, where you do not apply a single excitation at the resonance peak, but you apply excitation at 2 frequencies just around the contact resonance. And then you look at the amplitude at these frequencies, and you try to keep them at the same level. That means a 0 amplitude difference between these values. What happens now if the contact resonance frequency is shifting because, for example, the mechanical interaction changes? Then you will get a shift from the solid to the dashed line of the resonance peak, and suddenly the amplitude at frequency 1 is not equal anymore to the amplitude at frequency 2. If you now have a feedback loop in it, you can change the excitation frequency F1 and F2 to F1 dash, F2 dash, parallel at the same amount, so that you get again amplitude 1 to be equal to amplitude 2. So having the same amplitude of them. And like that, you can reduce the influence of the contact resonance frequency on the PFM signal. The amplitude is still a measure of your piezo response, and the phase should become less disturbed by the topography. This dual frequency resonance tracking has been implemented by Zurich Instruments in their lock-in amplifiers, and there you need one of their lock-in amplifiers which have 2 PLLs involved, and then 2 lock-ins in it, and either of these two can be connected to either the CX controller or the controller of the C3000i or core AFM, and like that you can work with drive, flex, and core AFM with each of these guys to perform the DFRT PFM mode. One short example of this is the same sample that I showed before, and there I used 3 volts of amplitude of resonance. Here I'm now using only 500 millivolts about, or a bit less. And you still get a very nice phase contrast between the oppositely polarized domains. Frequency is again around 300 kilohertz because now I'm doing resonance tracking, so I don't have a fixed frequency, and image size is also here 3 micrometers. That should be a superscript. Other flavor of PFM is high voltage piezo response force microscopy. And why do you want to do that? As said, we have very small signals, only some tens of picometers, and sometimes they are very difficult to measure. And you can, of course, try to enlarge your amplitude above 10 volts to get a larger response. And instead of working at the contact resonance frequency. Working below off resonance sometimes has the advantage that it's a bit more straightforward to get it quantified than working at the resonance frequency. Another application for application of a higher voltage is often you want to polarize your sample by an electrical field. So you might well be able to see the polarization with a 5-volt amplitude and detect your PFM response, but sometimes you want to either polarize or repolarize your sample, and for that you might need a larger electrical field than what you can get with the plus minus 10 volts from the AFM. And with a high voltage amplifier, you can then apply this higher DC voltage and do either spectroscopy or lithography to look at when is polarization changing, or to actually polarize your sample in a desired way. Of course, if you implement high voltage PFM on your own instrument, take care, particularly if you're working with high voltage amplifiers that can apply also high frequencies. You have to take safety precautions for yourself, but also for your equipment, that you don't burn, that you don't get any injuries. Working with high voltages is nice, but if you have a voltage between tip and sample, you also get electrical fields, and these electrical fields cause electrostatic forces. If you do an AC measurement, also the electrostatic forces are oscillating, and this signal intermixes directly with your PFM response, and they are very difficult to separate. And one way to now do it, because if you do spectroscopy, you want to look at which voltage do I see a polarization change. When is my sample getting polarized? But if at the same time I apply a DC voltage, I introduce the electrostatic forces, and that's what you don't want. So that's one way to circumvent that, is to work with so-called switching spectroscopy, where you have your AC voltage, and on top of that you make steps of a DC voltage, and then you step back to 0. And in the on state, of course, you have your electrostatic contribution, but in between you have areas without the applied DC voltage, and you can keep your electrostatic contribution in the measurement down. And you can do that in this way, starting, for example, in this case at very low voltages, step to high voltages and back down, and you can look what is the response doing. So instead of measuring while you are applying a DC voltage, you measure it after it, and many samples they will get polarized by applying the voltage, but they don't depolarize immediately when you put the field back to 0. Here you see a sample. It's a polymer thin film on a conductive substrate, and here you see the off field, so that the PFM response when we are not applying a field, but after pulses of different heights, and this shows the amplitude in a so-called butter-shaped light form, so a butterfly curve, and here the polarization, where you see the reversion here a bit below 20 volts to go up and a bit below minus 20 volts to go down. So this gives you immediate information about at which voltage can I polarize my sample. And here's on this example, you also see that the standard plus minus 10 volt is hardly enough to polarize this sample. So you really need this high voltage amplifier to get beyond those values. And what you can also see, the phase is nicely flipping from minus 90 to plus 90 degrees. Again, this is without any normalization afterwards. This is just an offset correction, but for the rest, nothing done with the phase value. And once you know that, you can do the so-called outbox inbox experiments or box out box in experiments, where you can polarize your sample as you desire. An area of 4 times 4 micrometers, and inside an area of 3 times 3 micrometers was scanned at a voltage of plus 40 volts, then a 2 times 2 micrometer area scanned at a voltage of minus 40, and there a center area of 1 square micrometer, again at plus 40 volts. And after that, I recorded a 4 micrometer image again, and outside you see the sample is not activated. I have a very low amplitude, the dark color. This is again a projection image, and you see there the positive polarization, the negative and the positive. What you nicely also see is that the domains here of the negatively polarized grains, they go nicely into the positive ones. So even though the movement was turned around there, you see that the repolarization into the green is extending towards the outside. So you can here nicely study these borders between oppositely polarized domains and the shape of the domains. You can also do this as a single point, so you can go down to a point, polarize that point, and then afterwards look how is the polarization at that single point change, and how does the border between that point and the surrounding look like. I already mentioned in the beginning there that I would come back to quantitative measurements and vector PFM. If you want to do that, it requires conversion from the measured signals, which are obviously in volts, into picometers. If you're working off resonance, and let's start with the out of plane, that is the simplest one. With off resonance, the normal deflection sensitivity can be assumed to hold. That means I can measure that, do the thermal tune, measure the spring constant based on Sader, use the equipartition theorem to get the deflection sensitivity, and then you get a good measure of how the deflection is transferred from volts into picometers. At resonance, you have to take the quality factor into account, but also the different deflection sensitivity of the off resonance signal. One way to quantify here would be to have the same sample measured both at off resonance and in resonance, and then get the product of the quality factor and the deflection sensitivity out of that. Because if you have the same material, the same amplitude, you know that you know from this measurement what the amplitude is in picometers, and then you can try to convert this signal by the same factor, or you can use the correction factor between the two. In plane, you need the lateral deflection sensitivity. In principle, that can be done in a very similar way. So also John Sader and his group also developed a method to calculate the lateral spring constant from the thermal tune. And if you have that, again, the equipartition theorem also for a lateral motion holds, and then you can also get the lateral deflection sensitivity out, which allows you to get the lateral deflection also into picometers. If you want to have it full in plane, you need to rotate your sample by 90 degrees and try to find the same position on the sample. Try to get some topographical features in it so that you can nicely recognize that you are at the same area. And then you have the lateral deflection in both orientation, and you can get the total in-plane deflection out. If you have only a sample with in-plane component, the vertical deflection might be of the buckling movement might be derived from these two measurements as well. But that is getting tricky because it's again a buckling movement which has a different deflection sensitivity than the deflection sensitivity that you would have for the off resonance case. So it's not just taking, I feel so many nanometers per volt, I use the same factor, that factor is not holding. And otherwise it can be tricky to get the in-plane component away from the out-of-plane component. Some pitfalls, I mentioned it already with the switching spectroscopy. Electrostatics can play a role. When you apply an electrical field, you have electrostatics working on the cantilever. Interestingly, they mainly work at the belly of the cantilever and not at the tip, because the tip is in contact with the surface and you cannot really push it in or out. Generally, the piezo materials are relatively hard. But nevertheless, there is that electrostatic contribution, and that will easily ruin your phase contrast of 180 degrees. Using stiffer cantilever helps. If you use stiffer cantilevers, the electrostatics will give you less bending of the cantilever, but the piezo force is generally of the sample is generally hard enough that you can still see the piezo amplitude. So that is hardly affected by the stiffer cantilever, but the electrical contribution goes down. Of course, if you go too stiff, you're working in static mode, you suffer more from tip wear and you may damage your sample if the sample is fragile. So as mentioned, apply switching spectroscopy instead of just a triangular ramping that you would normally use in spectroscopy. And the very first image that I showed, the first example, was actually done by focusing the laser not at the free end, but at the center of the cantilever. The other images were all with the laser more towards the end. But in this case, we applied the AC voltage to the tip and then focused the laser more in the center of the cantilever. And at that position, there is a position where the belly movement of the buckling caused by the electrostatics hardly gives any angular change. And that means that the only angular change that you can measure is caused by the PFM effect. And when we put the laser at the right position, we immediately got that 180 degrees and a constant amplitude independent of the polarization. If the laser is at a different position, you would see a smaller phase change between the two areas, between the oppositely polarized bands, and you would start to see an amplitude difference between the two bands. Electrostatics works by the field itself, but also be aware of surface charging. Piezoelectric materials are insulating. That means if you put a tip on top and you apply a large voltage, you may introduce a surface charge. If you introduce a surface charge, that may affect the electrical field through the sample, just thus affecting your PFM response. But what we have seen is if you afterwards, particularly if you are scanning and such a charged area is getting under the cantilever, it also affects the piezo of the electrostatic contribution into the cantilever signal. Crosstalk, we are working with only a few tens of picometers, and one might easily catch crosstalk. What we found is that in general, sample excitation is much less susceptible to crosstalk than tip excitation. So the first measurement where we put the laser in the center, that was with tip excitation. The rest was done with sample excitation, and there you got a much cleaner one and independent, almost independent where the laser was. You got the 180 degrees phase shift. So you're much less susceptible to crosstalk when you can apply your AC signal to the sample. High voltage, first of course, watch out for personal harm, but also take care that if you have a conductive substrate or and your tip is immediately in contact with that substrate, you have a low resistance with a high voltage. That's not a good combination. Also, your sample may have breakdown voltages. If you hit the limit there, you can create a spark and you may damage electronics, which is never a good idea. With that, I would like to conclude my presentation. I hope I've given you some insight in some of the background of PFM, how we implement it in ours, and give you some example to give you some ideas of what can be done with our instruments for piezo response force microscopy. And I hand over to
thank you,
Daniel.
Thank you, Patrick, for preparing that very comprehensive overview. It was a lot of application examples, very interesting stuff. Just to let everyone know, we recorded the presentation and we will make it available probably early next week. So if you want to watch it again, please do so. And if you then have more questions, feel free to contact us. And now we already have a few questions lined up. So let's get started right away. Here's the first question for you. Can you give some insight on the sample preparation technique for PFM analysis of nanocomposite based materials?
What based materials?
Nanocomposite based materials.
Okay. So the samples that I used so far, either they were on a highly doped silicon wafer that is well conductive, and then we put the silicon wafer was sufficiently large that we could clamp 2 metal clamps on it and then testing that there is a conductive connection between the wafer and the clamp to get an electrical connection to the substrate below the sample. I know it's also possible to put the samples, for example, on a gold coated wafer piece where you have an even better electrical conduction without the oxide layer that you intrinsically have on your silicon wafer. And once you have that, it is relatively straightforward. We can apply the AC or DC voltage either to the tip, or we can apply it through a connector that we have on the sample holder. And like that, you have your sample with the electrical field applied between tip and substrate and can do the PFM measurement. So I'm not sure whether that answers the question sufficiently. The sample preparation is always one of the most complex parts of AFM.
We'll see. We'll get a follow-up if not. And this is half a follow-up actually. How would I know whether my sample requires in-plane or out-of-plane analysis?
That's a good question. It's probably trial and error. So I would normally start with the out-of-plane measurement and see whether I there have my response. And I mean, you can then always also look at the in-plane contribution. If there is an in-plane contribution, then obviously you have to analyze it. I think from many materials, it is a bit known from literature whether they give you in plane or out of plane contributions.
Okay, so no clear rules there.
No, I don't think so.
Okay, next question. How can we get data on magnitude of piezo response in picometers per volt?
So if you have your signal in, so if you have your sample on a gold substrate, you can assume that there is no electrical field decay between the tip and the sample, and not between the sample and the substrate. And then you can immediately derive the amplitude measured by the lock-in, including the conversion factor, including the deflection sensitivity, and divide that by the amplitude of the excitation. What's often done is that you apply different amplitudes of excitation to see how the response in picometers is increased at increasing AC voltage, and then that gives you a linear correlation, and from the slope of that correlation you get your sensitivity in picometers per volt. You can calculate that back. Of course, it does require that you know the deflection sensitivity.
Yeah. Okay. Moving on. What are special precautions for sample preparation? Unlike AFM, many times instead of micro, people deposit samples on glass slides. Is it okay to prepare a sample of glass slides for PFM analysis?
I know it is done for the 2D materials, but otherwise, normally for PFM, a glass slide is only good if you can have a conductive coating on top. Otherwise, you will have a large part of your electrical field decay through the glass and not through your piezoelectric film in which you're interested. And if you don't know the electrical constants, you don't even know exactly which part of the field is in the glass and which part of the field is over your sample. And then you have a very hard time to quantify, to do any quantification of your signal. Plus, you will lose a large amount of signal. If your sample is a few hundred or a few micrometers thick and you have a 1 millimeter thick glass slide, of course, most of the field is in the glass slide and not over the sample. So you have only a very little piezo response left.
Okay. Next question. How do we merge the in-plane and out-of-plane response of PFM as a single vector output?
That is a good question. So first of all, you can not add apples to pears. So you cannot have the voltage of the vertical one, compare that with the voltage of the lateral one. Everything needs to be in the same units. And the moment that you can get all your signals in picometers, that you know also your out of plane, or the vertical deflection caused by in-plane signal, including the buckling sensitivity, that you can get that out of it, then you can get a complete vector direction of your PFM response. I think there are a few groups who know how to do it, but the calibration procedure is cumbersome, and I think there will often be a lot of assumptions. For example, if you can assume that your out of plane contribution is much larger than the in plane, then of course you can most likely neglect the in plane contribution in the vertical deflection. that makes life a lot easier. Then you can get your out of plane vector, your in plane vector by rotating the sample 90 degrees. That's then just a simple Pythagoras calculation for every point, having the lateral deflections added up at 0 and 90 degrees. And on top of that, you have your vertical one, which is also added by Pythagoras. And the angle, yeah, it's normal vector calculations, having separate vectors in each direction, which you derive into the complete vector. It is possible, but I don't think it's trivial.
Okay. Yeah, it doesn't sound like it. How do we measure the effective D33 value?
As mentioned before, if you want to get the D33 value, you look at the amplitude of the PFM response at different excitation amplitudes, and you then look at the slope of that signal. How is the PFM amplitude increasing with excitation amplitude? Keep in mind, if you put it on doped silicon and your sample is only in the same order of magnitude of thickness as the native oxide layer of the silicon, your voltage decay is not only over your sample but also over the oxide layer, which makes it very difficult to get your real D33 value out, because you don't know exactly which part of the electrical field is over the sample and which part is over the oxide layer of the substrate.
Mm-hmm. Moving on. How do we choose the AC excitation bias to get the PFM response? What precautions should we take to choose the excitation bias and also the resonance frequency?
So that's a few questions.
Can you do it in 3 minutes?
Yeah. So the AC voltage, I would generally start cautious with a few volts and look whether you see a response in the second lock-in of the PFM response. If not, increase the voltage stepwise until you see a better response, and then play with it. Precautions you have to take there is, if you have very thin samples, even an 8-volt or 10-volt applied voltage may actually cause a polarization of your sample. If that causes a polarization, and your sample of your voltage has to stay below this polarization voltage. So that is a precaution you have to take. For the resonance frequency, what I do is I take a thermal tune spectrum of the cantilever with the cantilever in contact with the surface. That gives me immediately the contact resonance, and I can set that resonance frequency as the frequency for the second lock-in and measure at that frequency. And if I like, I can even try to optimize this signal during scanning by making small steps in the excitation amplitude and see whether my amplitude is increasing. The closer to the resonance frequency, the higher the amplitude will be.
Okay.
So was that inside the 3 minutes?
That was, I think, about 1.5. So gives us time for one last question, I think. It's also the last one in queue. There's still one open from a gentleman who I think we're going to be in email contact with for some more extensive discussion. So I'll skip that one. Hope that's all right. And here's the last question for now. Can we deposit films, electrospun samples on ITO, FTO coated glass?
Yes, I would say you can work with ITO yes, that should work. I'm not a chemist, but if the chemical deposition, if that works to get the film on there, that should work.
Great. Then I think we'll wrap it up. Thanks to the audience for your interesting questions and for sticking with us to exactly the end. It's 3 o'clock now here in Liestal. Hope you have a good day, everyone. Thank you, Patrick, for the presentation and for your time answering the questions. And again, this will be recorded or has been recorded. We'll be sending you the link shortly. Watch it again. Let us know if you want to know more about PFM on any of our instruments. And we hope to see you soon at one of the next webinars. Goodbye.
Goodbye.